Great. Well, thank you so much, Dave. Thank you for the introduction and for the invitation. I really appreciate it. And thanks to everybody for sharing some of your Valentine's Day with me. The opportunity to talk about some of this recent research. The picture on the title slide is not just a Valentine's Day pun, but the chocolates within it are a bit of a clue to the construction that will underlie today's work. So, um, okay, so the work I want to talk about today is joint with Mike Davis, Jingyin Huang, Danny Ruberman, and Nathan Sanukian. So, it's been a pleasure to get to work on this project with them. And I came over later, I may just abbreviate just my last initials. We'll see. Okay. So to set the stage, I want to start with a very zoomed out question, uh, which is, what principles govern the topology of a manifold, right? Um, in dimensions that are low dimensions 1 through 3, especially dimensions 2 and 3, we tend to think of geometry as dominating, right? In dimensions 2, you can use things like Gauss-Bonnet, you have Riemann surfaces, you can look at manifolds as complex, or you can look at surfaces as complex manifolds, or looking at it geometrically in terms of, hyperbolic, spherical, flat. And then, of course, in dimension 3, that works through the geometrization program, Parallels proof of that. And in contrast, we know that in higher dimensions, algebra tends to dominate. And the buzzwords, the sort of key machinery that works very well is algebraic topology, in particular, things like the Whitney trick available in higher dimensions, which leads to powerful applications of surgery theory and all of the types of tools that go with it. And so the question is, what happens in dimension 4? We don't really know. We know that from the topological perspective, manifolds up to homeomorphism behaves much more like higher dimensions, but in the smooth setting, we don't have as much input from geometry to constrain phenomena. Okay. So we don't really know. But one question you could ask, and this is maybe sort of a historical way of framing it, but there's a question of Borel, which we'll look at more closely, but you could interpret this question as basically saying, do closed aspherical manifolds exhibit the same topological rigidity as geometric manifolds? So we know that the type of rigidity exhibited by geometric manifolds in low dimensions really constrains their topology overall. Perhaps in general, it might not be true, but maybe for aspherical manifolds, that's true. Okay. I meant to mention, please don't hesitate to interrupt at any point with questions. But let's see, is this slide? Yeah, okay, great. So why would you wonder whether this type of rigidity exists? Well, if you look historically, regardless of the dimension, really, if M and M prime are, for scare quotes, nice geometric quotients of Euclidean space, then even just homotopy equivalence between such manifolds generally implies diffeomorphism, or in the right context, even isometry. And so in particular, then they're also going to be determined by their fundamental group just by algebraic topological considerations, because if your quotient of Rn, then your only non-vanishing homotopy group is pi1, and you can show that pi1 determines the homotopy type. Okay, so what do I mean by nice geometric quotients? Well, surfaces, the Nielsen-Barr theorem would give you that. For flat manifolds, for example, n tori, this result goes back to Bieberbach. For hyperbolic manifolds, which think of as quotients of hyperbolic space, this is the famous Mostow rigidity. But it also goes back earlier to work of Mostow on solved manifolds. But they all sort of can be lumped into this mindset of nice geometric quotients of Rn, if you wish, and therefore a lot of their properties are related to the analysis of the actions of certain geometric groups on Euclidean space. Okay. So, just supposed to jump here? Sorry, let me just check one thing. Oh, sorry, I just got to double check one thing on my slides. Okay. For some reason, my slides are out of order, so let me jump forward. Sorry about that. So after after Mostow's work on solved manifolds in the early 50s, Borel writes to Sayre, and here's uh, a sample from that letter. It's in French, and um, this scan isn't so easy to read, so there's reproduction of it typed out here. And Borel's saying, this is surely you've heard of Mostow's work on this rigidity, and it's a beautiful phenomenon. He does say one thing, which my French isn't so good, so I checked what this means. I know this means the proof is something. So I plugged that into Google Translate, and apparently he thinks the proof is terrible. What's going on? Well, Borel's got some perhaps objections to the approach, but in particular, Borel says that while the theorem can't be trivialized, it could be simplified enormously by using covering space theory more. Okay. So you can already see Borel moving this towards a more algebraic perspective, and in particular, ends this paragraph by saying, perhaps this isn't just true for these geometric spaces, but is this true in general for compact classifying spaces? So that is, if I have aspherical spaces, k pi ones, that are compact manifolds. In particular, if they're homotopy equivalent, are they homeomorphic? So let's now go back for a moment to remind ourselves of what aspherical spaces are. So by definition, a space is aspherical if its only non-vanishing homotopy group is its fundamental group. Okay. So for CW complexes, aspherical is just the same as, or if you're connected, then aspherical is the same as having a contractible universal cover. So that I outlined this before when we were talking about geometric manifolds, but here the point is that because all the higher homotopy groups vanish, the weak homotopy type, and therefore the homotopy type in the case of CW complexes, is going to be determined by pi 1. Okay. And so that means that when you look at the universal cover, it's going to have all vanishing homotopy groups be weakly homotopy equivalent to a point, and therefore homotopy equivalent to a point. Okay. So as I also just said out loud, that also means that the manifold is determined up to homotopy equivalence by its fundamental group. Okay. And not only that, but even homotopy equivalences themselves are maps into it, determined up to homotopy by the induced map on fundamental group. So we should think about these as very algebraically rigid. And the question is, are they also topologically rigid? This is essentially Borel's question. Okay. Okay. So just to reiterate, some examples of aspherical spaces are sort of by definition in k pi 1. But for example, if you take your group to be Z2, you're going to get something like RP infinity. So, in general, an arbitrary aspherical space is typically not going to be a manifold, nor is it necessarily a compact, even if it is a manifold. But among manifolds, and sorry to put a bunch of text on the screen all at once, but all the spaces we were considering before are examples. So in dimension 2, surfaces except the 2-sphere and RP2 will be aspherical. In dimension 3, it's a consequence of the sphere theorem that all closed orientable irreducible manifolds besides S1 cross S2 that have infinite pi 1, those will all be aspherical. Tori are good examples in arbitrary dimensions of aspherical manifolds. And hyperbolic manifolds, you said this before, as well as solved manifolds. Okay. So part of the point of this list is to say, well, Borel's thinking about the relationship between what you see for geometric manifolds versus aspherical manifolds. Many of the natural examples we have of aspherical manifolds are already coming from geometric quotients of Euclidean space as is. Okay. Now I'll mention this a bit later, but there are indeed examples of closed aspherical manifolds which are not covered by Euclidean space. Mike Davis gave the first examples, and the construction that he used is going to play a key role in the main results today. Okay, so just to formalize it, so what was Borel's conjecture? As stated in that letter, the conjecture is that for closed aspherical manifolds, the homotopy type of the manifold determines its homeomorphism type. Okay. So we now know that this is true for closed orientable spherical manifolds, dimension less than or equal to 3. And there it's even true up to diffeomorphism because of the relationship between homeomorphism and diffeomorphism in low dimensions. And in particular, uses in the three-dimensional case geometrization. This is also true in higher dimensions, not using geometric techniques or anything like in dimension 3, using algebraic techniques. It's true for some fundamental groups, but it's open in general. So it's not known in general whether the Bell conjecture is true, but it's an important open question. All right. So now it's true that in Borel's letter to Sayre, they did ask, and we saw it on the paper, if the manifolds are homotopy equivalent, does that imply homeomorphism? But at the time, there wasn't a known difference between homeomorphism and diffeomorphism, right? So it wasn't until a few years later, with the introduction of Milnor's exotic spheres, that we even knew there was a difference. And so apparently, Borel later was quite glad that he framed it as homeomorphism, because it turns out if you ask the same question in the smooth case, that is, if you have smooth closed aspherical manifolds, does homotopy equivalence imply diffeomorphism? There, the answer is no. It is true in low dimensions, but it turns out to be false in all dimensions 5 and above. Okay. So the first examples, counterexamples, come from, for example, the exotic 7-dimensional spheres. If you connect some exotic 7 sphere with just the 7-dimensional torus, you'll get an exotic 7-dimensional torus. So it's going to be homotopy equivalent, in particular homeomorphic, but not diffeomorphic to the standard torus. So it was known that this would be false nearly from the moment that we knew that there were any exotic spheres in higher dimensions. But it turns out actually in all dimensions 5 and above, not just 7, there are exotic smooth structures on tori. So this is really robustly false in all higher dimensions. And that's been known since work of, I believe it's Shang and Wall in the 60s. Okay, so where does that leave us? Well, this question is not the exact question that Burrell asked, but I do think that part of the reason why it's interesting is because it really probes the breakdown of exotic phenomena and asks, as you restrict to simpler and simpler algebraic topology, do you get any topological, smooth rigidity? Okay. And despite being known to be false in high dimensions for a long time, we don't have, for example, exotic 4-dimensional tori yet that are known. So it's not as direct to construct counterexamples of dimension 4. And so the main result that I want to talk about today is that indeed in dimension 4, the smooth version of this question is also false. And so this is joint work with Davis, Huang, Ruberman, and Snukian, that there are closed aspherical 4 manifolds, we'll call them Q and Q prime for reasons that'll become clear later, that are homeomorphic but not diffeomorphic. Okay. So I'll pause there for a moment. I'm not sure. I can't remember if there are usually questions or anything in this case study virtual, but pause for 1 second just to process. Okay. So why is it harder in dimension 4? I shouldn't say harder. Why is it more elusive in dimension 4 than in higher dimensions to find exotic smooth structures on aspherical manifolds? Well, one problem is that the general approach to getting exotic copies in higher dimensions is in many cases to essentially understand somewhat globally the set of smooth structures on spaces. Whereas in dimension 4, we tend to sort of start with a fixed input manifold and then do some kind of operation on it to change its smooth structure. And the problem is that in dimension 4, when you have a non-simply connected form manifold, which in particular any sort of interesting, in particular any closed aspherical form manifold will have to be not just non-simply connected, but it'll have to have infinite pi one. Um, in general, in this case, our constructions for changing smooth structure, things like knot surgery, uh, we tend to no longer be guaranteed uh, that we won't be changing the homeomorphism type of the form manifold because we don't have, in general, uh, necessarily control over pi one. But even if we do, even if we can control the pi one before and after the surgery operation, we might not have input from the Escobar-Bordism theorem to show that the resulting manifolds are still homeomorphic. Um, so instead, we could think about what do we know? And we do know that there are exotic aspherical form manifolds that have non-empty boundary. Um, for example, there's even contractible ones. So a contractible manifold is certainly aspherical, uh, and there are examples of exotic smooth structures on contractible form manifolds due to, for example, work of Akblut and Ruberman. There are also other examples that'll come up later, which instead of being contractible have the homotopy type of, for example, a surface. So, form manifolds that are homotopy equivalent to a surface, since surfaces that aren't S2 or RP2 are aspherical, those form manifolds will also be aspherical. Okay. But if you have a form manifold with boundary, now we need to find some way to close it up. And the problem is that extending the constructions of exotic aspherical form manifolds with boundary to closed setting usually breaks either the exotic smooth structures or the fact that the manifolds are aspherical. Okay. So just for sort of a reductive, cartoonish demonstration of the problem, if we start with, let's say, a contractible, but really sort of any aspherical two-manifold with boundary, here we have a disk. It's contractible, so it's definitely spherical. The natural way of trying to get a closed surface from the disk would be to take two copies of the disk and glue them together along the boundary. But of course, that gives you S2, which is as spherical as it gets, not aspherical, as spherical as it gets. And you have this problem often, in all dimensions, that you can sort of pick up spherical topology when you try to glue a manifold with boundary either to itself or even to another simple four manifold with boundary. And the second problem is in terms of the exotic structure, it also tends to be the case that if you glue a four manifold or two different four manifolds with different exotic smooth structures to double them or twisted doubles glue them to mirrors of each other, you tend to wipe out the exotic smooth structure. So as an example, the sort of in all known cases where you have corks, if you take their doubles and twisted doubles, you generally get S4. So the exotic smooth structure tends to dissolve. Okay. Okay. So the approach then is going to be to still start with exotic smooth structures on a spherical form manifolds. In particular, we're going to start with some compact four manifolds that are aspherical, and in particular are homotopy equivalent to the two-dimensional torus. And then we're going to close them up to get closed four manifolds using what's called the reflection group trick, this construction from the study of Coxeter groups, which was used by Davis to construct the first examples of closed aspherical manifolds that weren't covered by Euclidean space. So that's going to be our strategy. And so what I want to do with the rest of the time today is start by giving an outline of this reflection group trick, because it's a really beautiful technique. And I think it'll help ground this construction. And then after that, I'll talk about how to apply it to the actual examples that we want. Okay. Okay. So I'm just pausing for questions, so I'll pause for that in a moment, but okay, don't need to pause. Okay, so let's talk about the reflection group trick. Um, this was first introduced by Davis in '83. And so what it's going to start with is what I'll call an input manifold. So it's going to be some compact manifold with boundary. And this construction is going to work in all dimensions. And so you're going to want this input manifold to have the dimension of the ambient manifold you want to construct. So if us, in our case, we want a four manifold, we want X to be some four manifold with boundary. But we not only need it to have boundary, we need to have a triangulation of the boundary. And it has to have a certain condition called the flag condition. And what is a flag triangulation? It's just a triangulation where anytime you see a collection of n vertices that are pairwise connected by edges, then it actually needs to span a simplex. So for example, if I have just the usual triangle as X, which, surface, so X would be two-dimensional, its boundary would be S1, but the triangulation on the boundary of a triangle, every vertex is pairwise connected to the other two vertices. However, those three vertices do not span a two-simplex in the boundary. They span a two-simplex, which is the triangle itself, but not one in the boundary. So the simplest flag triangulation on the circle is the boundary of the square. So you need four vertices and four edges. Okay. But in general, flag triangulations are easy to get. You can take barycentric subdivisions and easily get them. Okay. So once you have your chosen building block and a triangulation of its boundary, what Davis is going to do is assign it a right-angled Coxeter group. And it's a lot of words for what ends up being a really simple definition. For every vertex in the triangulation, you're going to get a generator. And then you're going to have two types of relations that are related to reflections, because these are related to reflection groups. Or, well, yeah, reflections. So the first is that every generator squares to one. You should think about that as, a reflection squaring to one. And then secondly, there's a few ways to write down this next relation, but we can think about it as saying that if you have two vertices that are joined by an edge, then their associated generators are going to commute. Okay. So this is also true if we're thinking about reflecting in the plane. If I reflect across the x-axis and then the y-axis, that's the same as reflecting across the y-axis and then the x-axis. So those are going to commute. Okay. So if I give you a concrete manifold with the concrete triangulation of its boundary, there's a simple group presentation we have here. We're going to do a concrete example in a moment with the unit square, but for now, let me just finish running through the sort of the workflow for this trick. So you get an input manifold with a triangulation. You get this associated Coxeter group. And then the next stop is this non-compact space called the Davis space. And what it is it's for every copy of, for every element in your Coxeter group, you're going to take a copy of your input manifold. So we're thinking about these input manifolds as sort of tiles, and you're going to take one tile for every element of this Coxeter group. And then you're going to end up gluing these different tiles across sort of, in a sense, faces in the triangulated boundary. I'll clarify that in a moment. But you should think about the boundary as having these sort of faces that you're going to be gluing and reflecting across. Okay. So you start with your one input copy of X, and then it turns out, I didn't mention it before, but it turns out that you can order this Coxeter group by the word length, essentially. And so we can think about these group elements as being ordered. And so you're sort of sequentially build up this non-compact space by just continuously gluing on a new copy of X according to the reflection across some face associated with some vertex. I'm intentionally being a bit vague there. And in reality, let me jump forward for 1 second. In reality, you actually switch from your triangulation to the dual polyhedral cellulation. So what you actually do is on the boundary, you switch from your triangulation where, let's say here I have four vertices of interest, red, green, blue, yellow. And I'm going to switch, this is a boundary of a ball. This is also a boundary of a ball. But now this vertex is replaced with its dual face or its dual cell in its face, the dual cell, the dual cell and the dual cellulation. So this is after switching to the dual cellulation, there's a natural way to now glue uh, copies of X to each other. Okay, we're going to do a concrete example, so I don't want to get caught up in the details there. But the next key point is that not only is this gluing determined by these elements of this Coxeter group, but the Coxeter group now acts on this space, on this infinite union. You can just take the basic definition that each one of these tiles is associated to a group element, and you're going to act on the tiles via the action of the group elements. Okay. And so finally, that's what we need. So we have this non-compact space formed from infinitely many copies of our input manifold, and it's not a closed manifold. So the final step in the construction is to pick a finite index torsion-free subgroup of this Coxeter group, and then take a quotient by it. Okay. So the finite index ensures that we're going to get a compact manifold in particular. And then the torsion-free condition guarantees that it's actually a manifold. And one thing that's nice is because of the particular construction, this choice of this right-angled Coxeter group, one can even just choose the commutator subgroup if one wants to pick a concrete example, but in different contexts, one could want to choose perhaps a different subgroup. Okay, so that's the general outline of this construction. But to drive it home, I want to look at a concrete example. So, oh, I forgot the punchline, which is, what does it have to do with aspherical manifolds? Start with that. I meant to say that if the input manifold is aspherical, then this larger space that you're building out of it, this Davis space d of x, and this quotient q of x, they are both aspherical. The basic idea is that it's more direct to show that d of x is aspherical based on its sort of step-by-step construction in terms of gluing pieces of this aspherical space to itself. And then the fact that q of x is aspherical comes from the fact that d of x is a cover of q of x. So if d of x is aspherical, it has a contractible universal cover. So q of x also has a contractible universal cover. Okay. So we saw before that the naive way of trying to take a two-dimensional disk and close it up to a closed surface did not yield an aspherical surface. It yielded the two-sphere. So let's try to run this reflection group trick with the two-dimensional disk as our input and see what happens. So in this case, we're instead going to view the two-dimensional disk as the boundary of the unit square. And here, I'm going to imagine I have some number of copies. Really, I have infinitely many copies of the unit square. And I've thickened and colored the edges so that we remember the triangulation. Okay. And so I like to think about this. My son is 1.5, and so we have a lot of these tiles that snap together. I don't know how visible I am on the screen. I'm small. But the idea is that we're going to take a bunch of these and glue them together. So we start with one copy, which will be the identity, like this, I guess. And the next step is we have to take a second copy and glue it to this first copy by a reflection across whatever side this corresponds to, or sorry, whichever vertex corresponds to. In our case, now we're responding to edges. So what I'm going to do is reflect this copy down. So they're now glued across the corresponding edges. And this is my first step. So if this was the identity element, this is the tile corresponding to reflecting across this side. Okay? And so that's A. If I call the bottom edge of this A, the next element after reflecting across is called A. If I reflect across the green edge, I'll get an element B. I'll call the green edge B. But now we have a bit of a dilemma. Or sorry, we can go ahead and reflect. I'll keep going. We reflect across the top edge, get another copy called C. Reflect across the yellow edge, get another copy called D. But now we hit a dilemma, which is if we want to reflect across A along the green edge and get another copy of our tile, it should be called AB because that's the word for this element in terms of reflections. But we also need that to snap in correctly over here, right? The identity reflect across to get B, and then reflect down to get to that tile. And why is this okay? Well, if you recall our definition of the Coxeter group, reflections that are adjacent are going to commute. So here, reflecting across A and then B is the same as reflecting across B and then A. So actually, there's no sort of issue. And indeed, this is what makes the gluing work with the definition of that Coxeter group. Okay. And so we keep doing this. We fill out AB, BC, CD, DA, and we keep going. And so if you keep doing this construction, because of the particular choice of the definition of the Coxeter group, it never closes up. It, in fact, gives you a tiling of R2. So there's some loud music outside. Enjoy. Okay, so the Davis space in this case turns out to be R2. And the set of the group actions, this Coxeter group, it acts by not by translation in the usual, how we might think about moving around in this lattice. Instead, it's acting by certain reflections. But you can check that it turns out that there's a fundamental domain. So let's try to think about what's identified here. Here we have, for example, if we keep going, A, B, C, and D. This is going to, oh, do I want to say this part? Yeah, actually, sorry. So let me just clarify what's on this slide. What's on this slide. So that was gamma. But now we want to choose a finite index subgroup, which we said we could choose the commutator subgroup. So if we do that, then once we mod out by the commutator subgroup, everything is going to commute. And so, for example, ABCD is going to be the same as BCAD. It's going to be the same as CDAB, same as DACB. And what we'll see is that we'll get, if we restrict the action of the or the quotient by the commutator subgroup, our fundamental domain will just be 16 copies of our tile. Okay. And if we remember the gluing information, I'm not saying you should do this on the fly, but you can do it. It's a nice little exercise. All of the edges on these tiles on the right side are glued to the ones on the left, and the top here to the bottom. And so what do we get? We get a torus. Okay. So in this concrete example, the reflection group trick, if we take our input as the unit square, our data space is R2, and our quotient space is the 2 torus. So this is a really concrete, satisfying construction, even though it might look sort of lost in some strange algebra or some Coxeter group. All right, so now I want to pivot to the proof of the main theorem. So just to remind you, the statement is that there's closed aspherical four manifolds, Q and Q prime, that are homeomorphic but not diffeomorphic. And so to flesh out the strategy that I started saying before, our first step is to pick some suitable input four manifolds, X and X prime. And I'll clarify what I mean by suitable in a moment, but we'll need basically them to we'll need them to have properties to make the rest of the proof strategy work in a moment. The first thing I want to point out is once you've fixed these exotic four manifolds X and X prime that have boundary, well, the fact that they're homeomorphic means that their boundaries are homeomorphic. So in fact, their boundaries are diffeomorphic because they're three manifolds. So because you have these four manifolds with the same boundary, but with different smooth structures in their interiors, if we apply the reflection group trick to them and get Q of X and Q of X prime, those resulting spaces are automatically homeomorphic because the gluing information is purely along the boundary, and we're only changing the smooth structure on the interior. And so sort of on each tile, we just change the smooth structure. And so globally, we have preserved topological type, but potentially change the smooth structure on this quotient space Q of X and Q of X prime. Okay, so that's the first step. The next step is we would like to show directly that Q of X and Q of X prime are not diffeomorphic, but it's not easy to show that directly. So instead, what we can do is show that these non-compact Davis spaces are not diffeomorphic. And so we'll do that using some more sort of standard, if you will, four-dimensional topology tools, some handle body arguments, some a junction formula, genus constraints. But then how do we actually prove that Q of x and Q of x prime are not themselves diffeomorphic? Well, what remains to be shown is that any diffeomorphism between the quotient spaces would lift to a diffeomorphism between their covering spaces, these Davis spaces. Okay. And now this problem is really an algebraic one. This is a lifting problem. So in particular, this involves showing that a particular subgroup of the fundamental group of these quotient spaces is characteristic. This is part of what you need to sort of pass through the lifting criterion. So I'll say a few more words about all of these steps, but this is the rough flow. So we have this construction. We distinguish the covers using more standard arguments, and then we'll use some group theoretic arguments to pass step 3. Okay. So, all right, and we get a contradiction. Okay. So now what I want to do, if there's no questions or anything, is jump over to my slides. Slides will be a bit more flexible, and this part I want to be able to go and sort of more hands-on. So let me just quickly switch this. I'll stop my screen share. There we go. Okay. All right. So the properties that we say we want a certain type of input form manifold. So let me maybe clarify here. For the input form manifolds, these are going to follow from a construction of an earlier paper that I wrote with Lisa Piccirillo. I never know what to say what year this paper is from. We posted it on basically New Year's Eve, 2019, which is in hindsight a strange choice. So I'd say that's 2019 and some change. Okay. And so input manifolds are going to have the homotopy type of T2. So it's a pair of exotic form manifolds with boundary, such that they're homotopy equivalent to T2. The part of the special property of each of these, if I can pull this up real quick, is that we have a genus constraint on the piece X, the form manifold X. So every smooth torus embedded in X is null homologous. And on the other hand, for the exotic copy H2 of X prime, it's generated by a smooth torus. Okay, so I'll sketch the construction in a moment, but the one way to think about why these are different is that one of them has its homology generated by a torus, while the other one does not have any homologically essential smooth tori. Okay. And then the fourth condition, which it's not at all obvious yet what role this will play in the argument, but it's going to be essential, in fact, that both of these manifolds embed smoothly in the four-ball. Okay. So what are these manifolds? Well, each of them is constructed by taking the Maser quark. So I should say that the specific examples in the paper are slightly different from the example in the paper with the exotic aspherical manifolds. Our construction is very, very slightly different from the construction in the paper with Lisa Piccirillo. But the basic idea is the same. So you take the Maser quark, which is a contractible form manifold that has this involution on its boundary that fails to extend on to a diffeomorphism of the interior, but does extend to a homeomorphism of the interior. And you take this Maser quark, and you're going to attach along some knot K. Normally, what you would do if you see a knot in the boundary of a four manifold, if you wanted to attach something to it, oftentimes you would think about attaching a two-dimensional handle to it, right? That's like a two-dimensional disk thickened to become four-dimensional, attached with its boundary along a neighborhood of the knot. But instead, what we want is to attach, instead of a thickened disk, which would be a two-handle, we want to attach a thickened surface. So this over here is a punctured torus, so T2 minus an open disk times D2. So you can call this like a genus 1 handle, if you will. Okay. And so what does this mean? Well, if I'm attaching a, just scroll down here for a second for some scratch work. If I have a contractible manifold and I attach a punctured surface with boundary to it, then at the homotopy level, that's like taking a cone on the boundary. And so this space is homotopy equivalent to a torus. And so that gives you X. And I'll just write it here below. X prime is obtained from X by removing the interior of that quark and then re-gluing it using tau. And so since tau extends to a homeomorphism of the interior, this preserves the of the interior of C, this preserves the topological type, but potentially changes the smooth type of the surface of the four manifold. Okay. And so the properties that are useful about this knot is that this is not this does not immediately give the conclusion that we want, but it turns out that tau of K bounds a smooth two-disk in the interior of C. So if we take this manifold X prime, instead of thinking about cutting out C and regluing it, we could think about reattaching our genus 1 handle. Instead of attaching it along K, we could attach it along tau of K, and that'll have the same effect. And it turns out that tau of K bounds a two-dimensional disk in C. And so what that means is that for X prime, we see a D2 down here, and then we're attaching a thickened once punctured surface with boundary. And so if I glue this to a copy of that surface with boundary, I'll get a smooth torus that generates the homology of X prime. Okay, that's why this has this property, this fact that its homology is generated by a smooth torus. And then on the other hand, it turns out that X emits a Stein structure. And the junction formula implies that any T2 in X is null homologous. Smoothly embedded in X is null homologous. Okay, so I just wanted to, it's, this is more for experts at the moment for the particular construction. But the basic input is that we can explicitly construct a smooth torus in one of these four manifolds, and the other one you can obstruct a homologically essential smooth torus using just the adjunction inequality. Okay, so we've now got the building blocks that we want, x and x prime. And the final step is to, I have some notes to myself here. Um, the final step is to actually now obstruct the diffeomorphism between these. So we have x and x prime. We produced q of x. Well, actually, the construction gives us d of x and d of x prime. These cover q of x and q of x prime. And now what we want to show is that these are not diffeomorphic. We know that they're homeomorphic because the homeomorphism we said before is sort of tile by tile. And our first step is going to be to instead show that these are not diffeomorphic. Okay, so um, so how are we going to do that? So here we need to bring into play one of the key properties of Davis's construction, which I uh, sort of skirted under the rug before. And so, in fact, there's going to be two facts about his construction that we want to recall, one of which is going to help us, one of which is going to hurt us. Okay. So we said before that the uh, sort of tiles x1, x2, x3 in d of x. Oh, I said this wrong. Sorry. The tiles in d of x are ordered. So we can think about them as x1, x2, x3, etc. And this ordering, we said, was defined in terms of word length in gamma. Because gamma had a natural presentation in terms of the vertices of the triangulation. So it has the natural base, natural generated presentation, natural word length. And it turns out that this word length has a geometric consequence, which is that if we look at sort of partial union, if we look at the nth stage, just the union of the first n pieces, it turns out to be, I'll say diffeomorphic for simplicity. There's a little bit of uh, details to sort out here. It's sort of starts out natively as a PL diffeomorphism, but for the arguments, we can just treat it as a smooth diffeomorphism. It turns out to be the same as a boundary connect sum of these pieces. Basically, the idea is that each subsequent tile only meets the preceding tiles along a codimension zero disk in its boundary. Okay, so this is a really key fact about these, and this is part of how you prove that these spaces are aspherical, actually. So that's one good fact. So maybe I should put that in green for its good fact. But there's also a bad fact, which I swept under the rug before, which is that each xi is really plus or minus x. We were gluing these manifolds by reflections along portions of their boundary. And when you do that, in order to get an oriented gluing, you need to reverse orientation on one of your pieces. And so as you reflect across these different tiles, you're alternating the orientation essentially each time. And this is bad news from the perspective of our invariants coming from, gauge theory and floor homology, because while X, for example, was Stein, its mirror will probably not be Stein. And we won't, in particular, have an adjunction inequality to constrain the genus. So the way that the final step of this portion of the argument goes is that if we suppose now that there's a diffeomorphism from x prime, from d of x prime to d of x, right? Then I've got x primes here going into my space of data space for x. Okay. Okay, so let's see what we can say. If we had an honest diffeomorphism between x prime and x, we'd immediately have a contradiction because we know they're not diffeomorphic. What we do know is if we, for example, just look at one of these pieces, we know that there is a torus sitting in here. And it generates second homology. So if we have a diffeomorphism from d of x prime to d of x, then it's going to carry this torus somewhere in here, okay? So I'm just going to draw that in red, and I'll just wrap up this sketch quickly. So the point is there's some torus in here. And it's embedded, and it has to be non-trivial in homology. Now, we haven't met a contradiction yet because we're not saying that this torus sits embedded inside of one copy of X. If it did sit inside of a single copy of X, we'd get a contradiction. But fortunately, there's the property that we know that this T has to lie in some Pn. Because if the space is built out by these growing copies of X, it has to fit into finitely many copies of X. So at some nth stage, we will have absorbed our torus. And now that means that it sits inside of some boundary sum of copies of, let me actually, to be a bit more clear, it sits inside of some boundary sum of plus or minus copies of X. And so we still don't have a contradiction. However, because each one of these copies embeds into B4, which was one of the properties we said our four manifolds had, we can, and since for the sake of time, I'll just sketch the rest of this very briefly. We can absorb all but one of these summands into B4 just by attaching the complement of X inside of B4 back to X. So I glue on the complement of X inside of B4 to each of these copies to embed this into X or minus X. I actually don't care which one it is. So I'm getting this into a boundary sum of these, which is just a copy of plus or minus X. Okay. And so I'm just try to wrap this up quickly. So our point here is that we almost have a contradiction. Because we now have a smooth torus sitting inside of plus or minus X. The only problem is that we need to make sure that it's still homologically essential, that we didn't kill it. But the point is that it has to be homologically essential in one of these pieces. So whichever piece it's homologically essential in, kill all of the other pieces. Okay. And so we end up getting an essential torus generating, or an H2X, which is a contradiction there. And so this implies that d of x prime is not diffeomorphic to d of x. Okay. And so just to wrap it up, finally, to show all diffeomorphisms qx to qx prime lift to d of x to dx prime, what you need to show is that pi1 of d of x, that naturally sits as a subgroup, since d of x is a covering space of q of x, its fundamental group is a subgroup of the fundamental group of q of x. And so what you need to show is that it's characteristic. That is, you want to show that it's fixed by every automorphism of pi1 of q of x. And I could say more about the details there, but the reason is that we already have one homeomorphism between q of x and q of x prime. And so if we had a second one, in particular had a diffeomorphism, we can pull that back to get some automorphism of q of x itself. And understanding whether these do or don't lift to the covers becomes a question about automorphisms of pi1 of q of x itself. And so if we can show that the fundamental group of that covering space as a subgroup is characteristic, it's preserved under all these potential automorphisms, and hence all those automorphisms have to lift to the cover. And that argument I won't say anything about, but it involves a choice of a particularly nice triangulation on the boundary that ensures there are no torus subgroups in pi1 of q of x, except for the ones that actually come from the tiles x. Okay, so I'll stop it there. Sorry for running long, and thank you guys again for the attention today.
Okay. Are there questions for Kyle?
I have a question actually. Yeah, thanks for the talk. That was very nice. Um, does your argument actually show that the double of x prime is different from the double of x?
Thanks. Yeah, this is a good question. So the answer is it does not show that. Indeed, the doubles of x, and if you double x with itself, or even if you double it by gluing on to minus x prime, these all end up being diffeomorphic to each other. And it's really a consequence of, I think the way to think about it is the underlying quark twists that are making them different are themselves, if you did a twisted double, and sort of the extra handle that you've attached to the boundary of this quark before getting x, it doesn't actually interfere with the cancellation that collapses the double of the Maser quark or its twisted copy to S4. Like all of that happens with the extra T2 times D2. And so you really end up basically repeating the proof that makes the Maser quark double standard.
I mean, okay, yes, but how come, like, what fails in your argument?
Yeah, so this
Because
is
they look almost the same, like the x and
exactly.
yeah.
Yeah, so I think to me this is the interesting question, which is we know that if you take two four manifolds with boundary, the same boundary, like if you glue them all of their boundaries together, you can pass a lot of topology back and forth across the boundaries somehow to cancel things. It seems like the gluing that happens, do I have it on here? I don't have it here. The gluing that happens in Davis's construction, I said this briefly out loud, but I didn't write it down. Every time you glue on a copy of X, actually, it's better if I do a slightly different picture. Okay, well, that's fine. Every time I glue on a copy, it turns out that my new copy only hits my previous copies in a disk along its boundary.
Mm-hmm.
So that's part of why it looks like a connected sum every time you put on a new copy of X. And I think that that sort of constrains the amount of topology that can be interchanged across different copies, the amount of cancellation that can happen.
Oh, you can still put it into a ball. Like you can somehow make it into a ball
Yes.
without interfering with the red part.
Yes, it's totally counterintuitive because eventually all of the boundary will be completely absorbed because it's going to make contact with subsequent copies. So it's very counterintuitive, but that's right. You can always sort of mush the attaching region back into a small ball if you pause at any finite stage. Yeah,
Interesting. Thank you.
yeah, yeah. But thank you for the question because I think that gets to the core thing that really makes this whole thing run, which is that Davis's construction really limits the amount of uh, topology that could pass between the different copies because it limits the gluing region. Yeah.
So for this example, what's your pi one in the end?
Enormous. I suspect. I think that if one, because part of the thing is the number of generators alone grows with the number of vertices in your triangulation of the boundary.
Mm-hmm.
So I think that,
So how bad is your triangulation?
yeah, so it depends. I mean, Snappy could tell you concretely, but like, I think this is, I haven't checked this, but just I would expect, for example, I don't know if it's true that if you take like the product of four copies of the interval to get the four ball, I mean,
Mhm.
this is not going to work for this construction, but just an analogy with the unit disk giving you the torus, it feels morally like if you take the four ball as, interval to the fourth power, maybe this construction gives you something like the four torus, or at least some product of surfaces seems likely. And so there's like a pretty simple uh, input that already yields a large fundamental group. My guess would be that if you ask Snappy for like a triangulation, I think that I can't remember if I checked on these, but I think it's going to require several tetrahedra in the boundary of the three manifold, and you might need to further subdivide to make it flag. So I'm guessing it's probably got its generators. I would assume are at least like, I don't know, 30 at least or something.
Mhm.
Yeah, but it'd be interesting to make it more efficient, perhaps. That'd be